Hi everyone, today we are going to talk about decision trees, and a decision tree is a supervised learning algorithm much like other supervised learning algorithms like linear and logistic regression, k-nearest neighbors, support vector machines, and so on, and hence it can be used both for classification and regression tasks. So there are two important things which we should consider before we proceed further with our discussion about decision trees. The first thing is it is having a tree-like structure, which means that there are different types of nodes in a decision tree, like a root node, a terminal node, and an internal node. And at each node, a particular decision is taken, while the final decision is taken at the terminal nodes. The second important thing, or the second important characteristic about decision tree, is the non-parametric nature, which means that there is no assumption made about the error distribution. Like we have in linear regression, that the errors are normally distributed with a specified mean which is 0 and a constant variance which is sigma square. We don't need to make any such assumption about the error distribution in case we are talking about decision trees. So this is a small toy example over here which demonstrates where exactly which can where we can talk about decision tree, and you can see that this is a classification problem which we are showing over here. So it has three features like feature 1, 2 and 3, and features and attributes are used interchangeably in machine learning. So we can say that we have three attributes and we have a target variable over here which is discrete in nature. And those who know what a supervised learning algorithm is can easily find out that we have a binary classification problem to solve. So here we use decision trees to solve the problem. Since a decision tree will always have a tree-like structure, it's very important for us to find out the root node, because the construction of internal nodes and the terminal nodes will be dependent on how precisely we are able to find or determine the root node, and the root node could be any of the features like feature 1, 2 and 3. So let's say we try to say that feature 1 could be selected as a root node. Just for demonstration purposes, I am giving this as an example. Let's say feature 1 is our root node, then it will take two values. It can be either true and it can be either false. If it is true, then our data set will be divided into three components because it has only three true values. If it is false, the dataset will be divided into two components because the event of feature 1 being false occurs twice in the data. Now you can see we have a root node and we have the possibility to draw two internal nodes at the end of the edges. Now for the internal node over here, we can either select feature 2 and 3. So let's say if we select feature 2, then again feature 2 can take two values. It's either yes or it could be no, and then the data will be divided accordingly. And if we are selecting feature 3 over here, if we are selecting feature 3, then again based on the true and false nature, we iterate and create a decision tree and eventually arrive at a decision. So this is how a decision tree construction is supposed to look like. If we have to apply brute force and consider feature 1 as a root node, feature 2 as a root node, feature 3 as a root node, then the problem will become very complex. We may end up creating a lot of decision trees which we eventually don't even need. We just need one decision tree which will do the task for us based on the features and data which is given. So here we consider some splitting criteria into the decision making, and one of the very basic splitting criteria which we use for decision making, which is called as an entropy, is something which we will be discussing in this class. Any given attribute, entropy is the measure of randomness of that attribute. This is what an entropy means. The formula for entropy is given over here. This is the formula for entropy, and I refers to the number of classes which should be present. For instance, if we consider the data which we have over here, there are only two classes which are present in the data, with the probability of 1 being equal to 3 by 5, and probability of 0 being equal to 2 by 5. And if we try to find out what is the entropy of the entire data set, this is the entropy not of an attribute, but we are talking about the entire data set. It is equivalent to minus 2 by 5 log to the base 2, 2 by 5 minus 3 by 5 log to the base 2, 3 by 5. So it comes out to be, we need to find the entropy corresponding not only to the data but also corresponding to each available feature given in the data. Overall entropy of the data is calculated and we were able to find out the overall entropy is 0.971, but definitely we are interested in finding out the entropy corresponding to each of the individual feature 1, feature 2 and feature 3. So let's find out how we calculate the entropy corresponding to each of the individual features in detail. So we first consider the feature 1 and find out the distinct values corresponding to that feature. So feature 1 has two distinct values, true and false, and the distribution of, or the probability distribution of each of the distinct values corresponding to the target is found. Like if we consider the places where the feature 1 is true, we can see that it's always 1. And likewise, the instances when feature 1 is false, the target is always 0. So we try to find out the probabilities over here. Then we use the entropy formula corresponding to each of the distinct values. Now this tells us the entropy of feature 1 corresponding to the fact when feature 1 is equivalent to true. So this is the entropy we get over here. Likewise, we get the entropy when feature 1 is false, and we also try to find out the proportion of true and false in the data, or the proportion of distinct values in the data to get the overall entropy. Now we get the entropy corresponding to true, we get the entropy corresponding to false, we get the proportion of true and false in the data, and the overall entropy boils down to this. Like we multiply 3 by 5 with 0, which is the entropy corresponding to instance when feature 1 equal to true. We multiply 2 by 5 with 0 again, the entropy of feature 1 being equivalent to false, and the overall entropy comes out to be 0. Let's look carefully how we calculate the entropy corresponding to feature 2. Feature 2 can take two values. It can be either yes or no. And here is where a bit of randomness will come into picture. Corresponding to the instances when feature 2 is yes, we have one instance where it is 0, and there are two instances where it is actually 1. So the two instances being this, y being equal to feature 2 being equivalent to y and the target being 1, and the feature 2 being equivalent to y and the target being 1. Likewise, we can have feature 2 equivalent to y and the target is 0, which is present over, which we have written over here. So there are three instances of feature 2 being equivalent to y, out of which only once it is 0 and twice it is 1. Likewise, there are two instances of feature 2 being equivalent to n, of which one of it is 1 and the other one is 0. So we write half and half over here. We use the formula for entropy and calculate the entropy corresponding to this instance where feature 2 is corresponding to yes. So you see the probability 0 being calculated over here. So this is probability 0 and this is the probability 1 which is calculated. We find out the entropy corresponding to feature 2 being equivalent to y as 0.92, while the entropy corresponding to feature 2 equivalent to n is 1. We get the corresponding proportions for yes and no in the data as well, like 3 out of 5 times it was yes, 2 out of 5 times it was no, and eventually we are able to find out the overall entropy, which is nothing but 3 by 5 times 0.92 and 2 by 5 times 1, and the overall entropy corresponding to feature 2 is 0.952. When we discussed about the feature 1, the entropy was 0, but when we are considering the feature 2, it's 0.952. Let's move a step ahead and do the similar calculation for feature 3. Just for understanding purposes, this is how we calculated the entropy corresponding to each of the features. Like for feature 1, the entropy came out to be 0. Feature 2, the entropy came out to be 0.95. Same was the case with feature 3. So this is all about entropy, how we calculate when we have a data set given. And that's it about entropy, and hope this video helped. And in the next video we will be discussing more about information gain, which is another splitting criteria. Thank you.